Hello, my name is Kevin McLemore, and today I'm going to talk to you about concept in collision theory and probability. To give you a brief overview, collision theory is the fundamental concept in physical chemistry and physics that plays a critical role in understanding various natural phenomenon. This presentation aims to provide you with the insight into the key principle of collision theory, its mathematical foundation, and real-world application. So we'll be looking at a scenario where a fellow student is struggling to relate the figures in 1.11 and 1.12 with equation 1.42 in the textbook. Identify and explain the correlation between these two figures in this equation. So this equation is an equation of collision and collision theory. I wanted to show it first so you can get an idea of what all the variables. So when we go through these various figures, you'll see how these figures start to tie into the equation. So starting at figure 1.11, here we see two molecules or two figures. This figure introduced in the concept of impact parameter B, which is the distance between the initial velocity of two collision molecule type 1 and type 2. We have 1 and 2. And also um, the derivative as a maximum impact parameter of a collision to occur with the equal to the sum of the two molecules R1 and R2. So this is saying you would simply add the two radii. So let's look at an example of impact parameter coming from figure 1.1. Imagine two billiard balls on the billiard table. When one ball is struck by another, the impact parameter is the distance between the direction of motion of the two balls at the moment of collision. If the ball collide head-on, the impact parameter is zero. If they collide at an angle, the impact parameter is the perpendicular distance between the path. Problem. In a game of billiards, two balls collide. Ball A is moving to the right at a speed of 2 meters per second, and ball B is moving to the left at 2 meters per second. What is the impact parameter of B if they collide head on? The answer: when the ball collide head on, the impact parameter B is perpendicular distance between their path at the moment of collision. In this case, both balls are moving horizontally. The impact parameter is zero. So when talking about maximum impact parameters or impact parameters, we have this B max. Um, so in the context of collision theory, B max refers to the maximum allowed impact parameter of a collision to occur between the two particles or object. Impact parameter B is the perpendicular distance between the initial velocity or the path of two colliding entities. So what's the significance of this? Bmax is a critical concept when studying collisions because it defines the boundaries beyond which the collision between two entities is considered impossible. It depends on the size of the radii of the colliding entities. The larger the entity, the larger the Bmax will be. Example, going back to the billiard ball, consider two billiard balls, one with a radius of 1 centimeter and the other one with a radius of 2 centimeters. The maximum impact parameter Bmax of the collision between these balls is 1 plus 2, which will give us 3 centimeters. If the distance between their initial position is less than 3 centimeters when they collide, the collision occurs, otherwise they miss each other. So moving on to figure 1.12, this figure illustrates how a molecule of type 1 moves through a gas with a certain speed, average magnitude of relative velocity, sweep out of the cylinder volume with molecules of type 2 within this cylinder will be struck by the molecule of type 1. So if you recall the 1.14 1.42, the formula or equation from the second slide, we notice that there's other variables in that formula. This is because depending on certain variables or certain influence on that equation, it influences the collision rate between molecules. One of those um, influence is density of molecules. N2. Density of molecule N2 refers to the number of molecules of type 2 per unit volume. It qualifies as densely molecules are packed within a given space. In the context of collision theory, N2 represents the concentration of molecule of a certain type. Type 2 within a defined volume is typically expressed in units such as molecules per cubic meter, or molecules per meter squared, or molecule per liter. The significance of N2 is a critical parameter with analyzing the behavior of gases, chemical reaction, or molecular interaction within a confined space. It provides information about the concentration of a certain type of molecule and is fundamental in understanding reaction kinetics and gas properties. So let's look at density as a molecule in two example. With a gas chamber, imagine a closed gas chamber with a volume of 5 liters. Inside that chamber, there are 2 to the 33rd oxygen molecule, type 2. To calculate N2, we can use the formula below. N2 equal the number of molecules divided by the volume of the chamber. So by substituting the values, N2 equal 2 to the 10 to the 23rd power as far as molecules of oxygen divided by 5 liters, that will give you N2. Another factor that influences collision rate between molecules is time interval, and that's going to be designated as delta T. Time interval refers to the duration over which collision between particles or entities occur. They measure the time period during which interaction or event take place. In collision theory, delta T plays a critical role in determining the likelihood and frequency of collision between particles. It is typically expressed in units such as second or millisecond, depending on the context and the system being studied. So let's look at an example. Consider a chemical reaction taking place in a reaction vessel. Delta T of the reaction represents the total time during the reactant molecules collide from transient state and lead to product formation. For example, if the reaction proceeds for 10 seconds, the delta T is 10 seconds. The significant emphasize that T2 is a critical parameter when studying reaction kinetic molecule dynamics. It helps determine how often collision occur and how quickly the reaction proceed. So now we're going to look at equation 1.42 to calculate the number of collision. Again, this is the formula. So we have looked at the B max. We know the velocity. We looked at the velocity, and we looked at the density. We know these values have an impact on how molecules collide. And we also know from the two figures that when we're talking about, obviously, collision, we are talking about two particles or two masses. So let's look at the calculation or example. Let's consider this scenario involving two type of molecules, type 1 and type 2, with different size, and we want to calculate the number of collision during a certain observation time. Assume that Bmax of this system is 0.2 nanometers, N2 is 5 to the 10 to the power of 19 molecules meter cubed, and delta T is 0.1 meters a second. Use these values to calculate the number of collisions using equation 1.42. So let's summarize what we talked about. Um, we looked at fundamental concepts in collision theory, including impact parameter B and maximal impact parameter B max, density of molecules into as the concentration of molecules in a volume, time interval delta t as duration during the collision occur, and we tie this to equation 1.42, which quantifies the number of collision. These concepts help us understand how collision between particles or entity occur and influence various nature phenomena. Collision theory and probability are fundamentally principle with broad application in the physical science and engineering. Understanding how particles interact and collide is a key to advancing knowledge and solving problems. Thank you for your time and your patience. Now I'll be answering any questions.